Hello everyone. Till the last video we saw a couple of things. Basically we saw and learned a lot of things. So let us try to revise a bit. So we came up with a checklist first. We came up with some 5 to 6 points which said that these are the checklists that you need to that you need to fill out to quantify the quality of the clock tree that we are building. Next we used a very basic H tree algorithm to build a small clock tree for 16 clock endpoints, and this was that particular tree. And next what we did, we quantified this particular H tree against the quality check parameters and found out that there were a lot of problems with that. There were a lot of problems associated with this particular clock tree, and the major reason that we found out was the transition or the clock slew, the clock signal slew. The slew of the signal was very bad, and we were trying to find out means to solve this slew of the signal. Then we came up with a methodology which was like clock tree buffering methodology, which helped us to reduce the slew to a very good extent, and we were pretty much satisfied with the slew of the signal. So and also while building the clock tree, we came up with some certain observations. The observations were the levels of clock tree, the load that each level should be driving, and the type of the buffer at each levels. So what we'll do is all this, whatever we have learned, we'll try to implement on this particular clock tree, and let's see where we go. So let's try to do that first. So we had this particular wiring that we had done. Now we'll try to place the buffers, start placing the buffers, or start building the tree with the concepts that we have learned till now. So conceptually whatever we have learned, we'll try to implement on this particular tree. So the first thing that we learned was we have to buffer this particular tree. So this is the buffering that we are starting point. So each buffer will drive one flop over here. So this had came up because of the load splitting that we had done in the last video. So each and every buffer is driving one particular flop. For example, there are like 1 2 3 4 and 4 into 4 16. There are 16 buffers which are driving each 16 clock pins of the flops. So to start with, we are buffering from this point. Next what we'll do is we'll place buffers over here. So these buffers will be driving the buffers which are driving the clock pins of the flop endpoint. So these are the buffers. These are supporting these two buffers. Similarly, this will be supporting these two buffers, and so on. So we need to provide one more support for these two buffers also. So let us try to do that. So these are the buffers that will be supporting these buffers. So this is again this kind of tree that we are doing, which we are doing a load splitting kind of thing over here, but to a very different level. So yeah, we have done the load splitting. We have put some more buffers over here to support these buffers, and we know the reason why are we doing this. We know the reason. We already had this in the last video where we introduce the concept of load splitting and how to create a buffer tree. Next, these two buffers will be supported by a chain of buffers which is placed over here, and finally we have the last trunk of the clock net which has to be supported, which has to support these two buffers. So let's do that. So now the clock signal will start from this endpoint, and it will jump through all these buffers and finally reach over here. But that is not the point. The point is we need to qualify this particular tree based on the quality check parameters that we had. But before that, let us try to do the same kind of observations that we did for the small clock tree in the last video. So these were the observations that we did. We had checked for levels of buffering. We had checked whether at every level each node is driving the same load, and also whether at every level the buffers are identical. So these are the kind of observations that we did in the last video. Let us try to do the same kind of observation for this tree also. So let us start with the first thing, which is the levels of buffering. So for levels of buffering, we need to identify how many how many jumps does the clock signal make before reaching to the clock endpoint. So in this case, the tree looks a bit complex. It is not as complex as we see in the recent VLSI chips, but it's a bit complex than the previous one. So let us try to do it a bit systematically. So what I'll do is we'll take this particular clock. While we count the levels over here, we will build an equivalent clock tree at this area. So let us try to do that. For example, so this is the level 1 of buffering. So what I've done is I've put this particular buffer over here to get a schematic of this particular thing, so that it will make things very clear. So this is the level 1 of buffering. So this is the level 1 which has got only one buffer. Next, you have the level 2 buffering. This is the level 2 buffer. So this is the level 2 of the buffering. This is similarly, this is the level 3 of the buffering. So first 3 levels are over here. So you can map whatever I draw over here with this particular schematic. So as I start increasing the levels of the buffer over here, so you can start mapping this particular levels with the schematic that I draw over here. Okay. So we have drawn 3 levels of buffering. Now the 4th level of buffering was this one. So at this particular net was driving this particular two buffers at the same time. So basically when a clock signal reaches over here at the next time period, it will reach at this point and this point at the same time. So hence these two buffers come at the same level, which I have drawn something like this over here. Okay, next we'll move to the next level. So level 5th buffering is present over here, which is this level 5 buffering. So why it is at the same level? So when this clock signal comes over here and the same clock signal comes over here, and at the next time period they will take a jump and reach over here, and at the same time the same clock signal will also reach at this point. Hence the level 5th of buffering are level 5 buffers are this ones. So we have drawn over here, these are the level 5 buffering. Let's move on. So these 4 buffers will be level 6 of buffering. So which means once the clock signal, which is present over here now and which is also present over here now, it moves ahead and reaches at this point, this point, this point, and this point at the same time. It roughly at the same time. Basically the same jump. It's over here. So this is the level 6 of level 6th buffering that we have done over here, and this is how it looks in the in the layout. This is how it looks in the schematic. This is the level 6 of buffering. Next will be the 7th level of buffering, which is nothing but the buffer that follows level 6. So it's just a serial arrangement of buffers. So this is level 7th of buffering. So it's becoming more complex. So let's try to slow it down and let's try to simplify it. Next, we have the level 8 of buffering. If you see at this point, this particular point, and this particular point, when the clock signal reaches and moves ahead, it will reach at the output this over here at this point, this and this. Basically it will cross the level 8 at the same time. So we have drawn all the level 8s over here. So level 8 has got 1 2 3 4 5 6 7 8 buffers, but this is called as level 8. And finally the 9th level of buffering, where each buffers are driving 2 more. So this buffer was driving 2 buffers, this is driving 2 buffers, this is driving 2, this is driving 2, and so on. So each buffers are driving 2 buffers. So there will be chain of 16 buffers over here, and this is the 9th level of buffering. So as and when you map this particular levels of buffering over here, things become more and more clear. So this we are aware of this kind of diagram. We have used this kind of diagram for the load splitting technique, to understand the load splitting technique. So this diagram is, we are very familiar with this diagram, but we are not familiar with this diagram. That's why I created a mapping schematic at the right side. So we have reached the 9th level of buffering over here. So the first observation, which was the levels of buffering, are this one. We have got 9 levels of buffering, and finally at the output of this buffers, they connect to the flops. So we have got 16 flop clock endpoints. These flops are nothing but which are placed over here, this point over here, over here, this, and so on. This particular white spots that we see over here, these are nothing but the flop clock endpoints, which are nothing but this clock pins which are marked by an arrow. So finally we reach at the clock after the 9th level of buffering, we reach the clock endpoint, and so the first observation that we did. So the first observation that we did that the levels of buffering. So if we count the levels of buffer, we have got 9 levels of buffering over here. So yeah, it was a bit complex, but imagine for a 16 flop, if it becomes a bit complex, imagine the amount of complexity that will be involved when we go for millions of flops, for buffering for millions of flops. So in that case, all these things are automated, but this is the basically the tech or the algorithm behind the automation. So if you try to understand what happens with a bunch of 16 flops, the same thing also applies, more or less the same thing also gets applied for the bunch of millions flops. So that's why we started with a 16 flop clock tree. Okay, the next observation is at every level, at each node should be driving the same load, and that's what we observe. We slightly observe over here. For example, let's say this particular node, it's roughly, or let's say at this particular level, which is level 4, the length of the wire are pretty much the same, and also the kind of the buffer, which is the third observation. We have maintained the same kind of buffer at this point at every level. So basically these 2 points are getting covered over here, which is identical buffering at the same level, and at every level we should each node should be seeing the same load. So at every level, first of all, we have used the same kind of buffer for the complete clock tree, not even in levels, but for the complete clock tree we have used the same size of buffers. That is the first assumption. So we are good with the second, we are good with third observation over here. And the second observation is that the length of the wire that every buffer at a particular level is driving is approximately the same. So for example, level 6, let us try to look into the level 6. So level 6 buffering, this one, so this particular buffer, and this one, they are all driving a length of the wire which is exactly the same. Okay, so this brings us to the third observation, which is that at every level each node should be driving the same load. So since I'm running out of time and we have also completed with this observation, we'll try to also conclude these observations maybe in the next video, and also come up with the checklist that we were trying to fill out, and we'll fill the checklist for the clock tree that we have built over here. So let us try to do all this in the next video. Thank you.